the interest of time, let me start. It is my great honor and pleasure in this anniversary of ours, the 10th Industry Spotlight organized by Santa Clara Valley section of IEEE and Computer Society chapter, to host Kim Keeton. And she'll be presenting the talk titled Memory Disaggregation, Thinking Outside of the Box. And so with no further ado, it's all yours, Kim. Would you like to please share the screen? And I will get off of the video and I will ask everyone else so that we can have improved experience. Thank you very much. Kim, everything's yours.
Excellent. Well, thank you so much for the invitation to come and speak today. I'd like to tell you a little bit more about some of the work that I've been doing for the last couple of years in the area of memory disaggregation. And so this is work that I've been doing in collaboration with my former colleagues at HPE, as well as collaborators at VMware Research and Microsoft Research, UT Austin, and ETH Zurich. So what's the problem we're trying to address? We're living in a world that is very data rich. There are more and more data sources, more and more applications generating more and more data. And we need to be able to access and process this data faster and faster, because we're trying to use the data to inform decisions that we're making, maybe even automating those decisions and allowing machines to make the decisions for us. Because we need those answers quickly, the urgency really kind of suggests that we need to be processing on data that's memory resident. And so there's a tension though, because the data keeps getting bigger and bigger. And so it gets harder and harder to make sure that all of that data can be memory resident. So that's just one of the problems. Another problem is that system balance isn't really keeping up. And so some recent data suggests that processors are increasingly, the ability of processors to process the data is actually outpacing the ability of processors to access the data. And so lest you think that this is a new set of challenges for us to deal with, I have a couple of thumbnails here of slides from a talk that I gave about 4 years ago, essentially giving the same kind of challenges that we face today.
Kim, it's in the Patterson-Hennessy book.
Excellent. Well, there you go. I am in good company then. So the good news is that there are technologies that are potentially going to help us out here. And in particular, network technologies are getting faster. And so we're seeing things like RDMA over InfiniBand or Ethernet, as well as emerging interconnect standards that are open, like Gen Z and Compute Express Link or CXL. And these interconnects are providing upwards of tens to hundreds of gigabytes per second worth of bandwidth, as well as sub-microsecond latencies for small transfers across the fabric. So that's great. And another key feature here is the ability to do one-sided accesses. In particular, that means that a processor can actually directly read or write the memory without needing to have a processor be involved on the far side across the network. So this constellation of features really allows us to think outside the box, both literally and figuratively, and to think about designing systems that disaggregate memory. So what do I mean by that? Well, essentially imagine a large high capacity pool of memory that's sitting on the network actually, and where compute nodes can actually access that memory across the network. So the benefits of this are multifold, right? So now compute nodes have the opportunity to access a lot more memory than they can fit inside of the single box that is their local box. These architectures also allow us to independently scale the compute from the memory system. And so both scaling as well as evolving the components over time. In order to add more memory into the system, we don't have to add another processor just to get its memory, even though we don't actually need the processor. And another benefit is that we have separate fault domains between the different components. So if a processor fails or a compute node fails, the state that it's written to the disaggregated memory is still going to be alive. And so it can potentially be picked up by another processing node in order to continue the computation. And we'll see the implications of that in one of the topics that I want to discuss. And finally, because the memory is equidistant from all of the different compute nodes, there's an opportunity for more sharing between the different compute nodes. So disaggregation isn't a new topic. It's something that people have been doing with storage disaggregation for a number of years. And in fact, many of the cloud environments that we have today that are commercially available, this is kind of the de facto standard of using storage disaggregation as a way of architecting those systems. What's new here is that we're trying to apply the notion of disaggregation to memory. So this is becoming a more and more popular topic in both academics circles as well as industrial circles. And so one example project that I'm familiar with, given my time at HPE, is the Machine Project. And so just to give you a little bit more detail about that, the Machine Project was a hardware software co-design project inside of HPE that resulted in a hardware prototype that had 160 terabytes of fabric attached memory. So that's pretty massive, right? And so 40 compute nodes were connected across a photonic interconnect using an early version of Gen Z to this large pool of shared disaggregated memory. In addition to the hardware, the program also looked at system software and developing an entire stack, as well as looking at a collection of different applications to just kind of explore what are the possibilities of this memory-driven computing model. And in particular, some of the results were quite impressive, actually, ranging from 1 or 2 orders of magnitude if you were working with existing frameworks like Spark, all the way up to 3 or 4 orders of magnitude if you were willing to rethink how you structured an application. This particular example was in a financial modeling kind of application where you could convert or pre-calculate a large number of simulation results into a lookup table, which then could be accessed much, much more quickly at runtime than actually doing the simulations in the path of the code. So tremendous opportunities here to really leverage this large shared pool of disaggregated memory. So the great promise, but there are also some challenges that remain. And in particular, disaggregated memory, even though the interconnects are quite fast, it's still about an order of magnitude slower to access data that's stored in far memory than it is to access data that's in the near memory, hence the name far versus near. So this is a challenge that we need to overcome. Second, we also need to then think about how we're going to allow sharing between the different compute nodes in the system. Traditionally, we have a single compute domain, a single compute node actually has hardware cache coherence support that can help it to support sharing within that compute node. There's not really any similar kind of support that happens between the different compute nodes. And then finally, accessing data in the far memory means that you're actually going to be transferring that data across the interconnect. And as we know, data movement is actually a very expensive operation. And in fact, it might not even be necessary depending on how we're going to use or whether we're going to use the data that's actually being transferred. So for the rest of the talk, I'm going to dive into these challenges a little bit more and talk about some potential solutions and ways to address these challenges, as well as exploring some opportunities that disaggregated memory architectures provide. And then if there's time, I'll also give a few thoughts on some open questions that are ripe for further investigation. So the elephant in the room, network latency is dominating disaggregated access times. Well, so let's rephrase this question a little bit. The way that programmers typically access memory is through data structures. So let's ask the question, what would it take to design data structures in a far memory environment? We can start by thinking about, can we borrow any techniques from traditional environments? Bearing in mind that we have to deal with this order of magnitude latency difference between far and near memory, as well as the lack of coherence support in the hardware between compute nodes. So if we think about it, neither near memory data structures or data structures that are designed for NUMA architectures really tick both of those boxes. Distributed data structures that are designed for clusters come closer, but they also make some assumptions that are not necessarily applicable in a far memory environment. In particular, they assume that memory is operated on by the local processor. So if node A wants to access memory on node B, what it has to do is to send a remote procedure call to node B, let node B actually operate and calculate the answer, and then send it back. So that makes sense in a distributed environment where we're talking about compute nodes, talking to other compute nodes, but it might not necessarily make sense in a far memory environment where the disaggregated memory doesn't actually have intelligence. Even if it does have intelligence, it's not clear that we necessarily want to be using the intelligence for the purposes of handling these remote procedure calls or two-sided operations. So as a result, some work that my colleagues and I did that was published in HotOS, we proposed to rethink how we design data structures for far memory environments. So what do we mean by a far memory data structure? Well, the canonical version of the data structure is stored in far memory or disaggregated memory. But then the compute nodes actually have the option of being able to cache portions of those data structures in their local compute node memory. So what we're calling near memory before. And so our idea here was that these caches are really comprised of data structure specific techniques for managing the data that's being cached. And that the caches are ephemeral in that when the application exits, the state will go away as well. A final component of farm memory data structures is the algorithm for how you're going to access the data in farm memory. How are you going to use the primitives that the interconnect and the memory itself provide? And then also, how are you going to actually manage the data that's being cached on the local nodes? To overcome that long farm memory latency, we're going to try to get to the point where we can actually do data structure operations that will complete in a constant number of farm memory accesses. Ideally, just one farm memory access. And in order to do that, we're going to have to trade off what we would normally do as a farm memory access and make it more of a near memory access. And we'll do that by trying to find ways of optimizing pointer chasing in the farm memory, trying to intelligently cache data in the near memory, and then finally trying to find a way of efficiently supporting sharing of the data that's being cached across the different nodes. And so for the purposes of this part of the talk, I'm just going to focus on those first two ideas. So clever data structures can, get you pretty close to what you might want to be able to do, but they're probably not going to be able to achieve that elusive goal of a single farm memory operation per data structure operation. In order to get closer to that goal, we're probably going to have to rely on a little bit of help from the hardware. So as a part of our HotOS paper, we proposed some very simple but general purpose hardware extensions that might be able to allow us to build better data structures in farm memory. And the idea was that by having a very narrow interface, they would be simple to implement, but by making them general purpose, they would work with a wide range of different data structures. And so in particular, we looked at various forms of indirect addressing, scatter gather, and notifications. So by indirect addressing, what I mean is the ability to dereference a pointer in one farm memory operation. So here, our target is the purple blob, which is the data that is of a specific length. But we're going to provide the address, and then we want the disaggregated memory to actually do this indirection for us. We can potentially think of adding an optional argument that's an optional offset that we might be able to add to the base address, as shown here in the middle, or an offset that we would add to the target of the pointer. And so there are these three different kinds of indirect addressing modes that we think will make sense for pointer-rich data structures. Now, in addition to these different addressing modes, we want to think about, what is it that we want to do to the purple blob? And so we might want to read it, we might want to update it in some way, or we might actually want to perform a simple arithmetic operation on it. And so we think that, all three of those types of accesses make sense for all of these different addressing modes. And in fact, even combinations of these different operations might make sense. So for example, you might have a fetch and add indirect, which would allow you to dereference and increment a pointer, which is also a common operation in pointer-based code. So this is one way that we could potentially accelerate our ability to deal with pointer-rich data structures. Another example of how we might be able to make our one farm memory request actually matter is to be able to use that farm memory request to access multiple different addresses in the farm memory. And so here, so this is typically referred to as scatter and gather. And so here we're looking at 4 different alternatives of that based on whether you're reading or writing the data from farm memory, and then also whether the addresses in farm memory are contiguous or discontiguous. So for example, read gather is that we're trying to read data from farm memory into the near memory, and we're gathering the data from discontiguous addresses into a contiguous buffer in the near memory. So now GenZ and RDMA, each support subsets of this set of operations, but we believe that it's useful to actually have the full complement of all these different operations in order to support things like strided access, or turning a row major data layout into a column major layout. So if we think about putting these things together, how can we design a data structure for farm memory? So let's take, for example, a map. A map is something that maps from a key to a value. And so typically maps are implemented as either hash tables or trees. So if we think about what would it mean to build a really, really large map using a hash table? Well, The good news is that we would get constant time accesses for read operations. But there are definitely issues in hash tables with collisions. And the typical way that we deal with those collisions, those things like chaining or inlining really don't necessarily play very well with far memory. Chaining requires lots of far memory accesses to chase pointers, and then inlining packs too much data together, and you will end up with amplification of your reads and writes. So that's not necessarily a good match. Additionally, when you try and resize a very, very large hash table, that can be very disruptive. So a hash table alone, probably not a great match for far memory. A tree, well, a tree has issues with traversing from the root of the tree to the leaf nodes where the data is stored. So, there would be a lot of far memory operations involved in a traversal. You could potentially cache those, cache some of those sort of operations. But in order to really eliminate them, you'll need to cache pretty much the entire data structure, which doesn't make a lot of sense if you're trying to build a really large data structure because near memory is limited, as we talked about earlier. So as a result, we don't think that either of these traditional data structures necessarily makes sense on its own. Instead, what we proposed in the HotOS paper was a combination of these data structures that we called a hash table tree or an HT tree. And the idea is basically we've got a tree where each of the leaf nodes of that tree is a hash table. And so this entire data structure would be stored in far memory. And then the data structure clients would cache the tree portion, the upper portion of the data structure in their near memory. So that then when they wanted to access data, they would use that local tree to navigate with entirely local operations to find the correct hash table, then calculate the hash offset so that they could find the right bucket, and then use an indirect accelerated operation in order to actually access the data that they care about. So in best case scenario, that's going to require only a single far memory access per read, which is great. It allows us to achieve with the goal that we had. If in fact we end up having issues with with collisions, as hash tables are known to have, the good news here is that now we don't have to worry about reorganizing the entire hash table, a really large data structure. It's a very localized operation on only the hash table that experienced the collision. So there's a far quicker way to actually remedy the collision actually in this data structure. So this is just kind of one example of how a clever data structure and a little bit of hardware support might allow us to achieve the goals that we have in terms of trying to reduce or overcome the latency challenges of a far memory environment. Moving on to our next challenge. Well, by now you're saying, well, but I know this is a great idea, Kim, but doesn't caching really muck up the works, really? So let's imagine that here we've got compute node 1 and compute node n are both trying to cache the same data structure, the red data structure here. Maybe that's the tree part of the HT tree that we just talked about. Well, unfortunately, what happens when compute node n makes a modification to that data structure? Then compute node 1 is going to find that the copy of data that's in its cache is now stale. And so as a result, it's not going to be able to use that if it wants to ensure that it's only accessing up-to-date data. It's going to have to either check the data that's in far memory or do something in order to detect that this problem occurred and then to remedy it. So what are some alternatives here? One alternative is to find a way of accelerating that notification that there's been some sort of an update. Another way is to design the system in such a way that we don't actually need the notifications. And I'll explain these both in a little bit more detail now. So the final primitive set that we proposed in the HotOS paper was a way to accelerate notifications. And so, normally, if a compute node wanted to know whether it had the most up-to-date data, it could repeatedly probe the far memory to understand, what was the most up-to-date version of the data. But that's costly, and we would like to avoid that where possible. And so, imagine if we could have, some sort of a callback that would be triggered only when that data changes, so that that we could sort of avoid this notion of repeated polling. Well, the primitives that we proposed actually were to basically have those notification mechanisms. So define a region of memory that you want to monitor, and then when an update occurs to that region, deliver that notification to the clients that requested it. And so there are variants of this that would allow you to invalidate stale cached data. You might even be able to, if the data is small enough, even return the updated data. so that the client could update the cached version of the data in its near memory. So that's one way that we could use notifications is, for managing our cached data. Another way that we could actually use the notifications would be to help with coordinating between clients that are running on different compute nodes. So imagine that, instead of just looking for any old change to this memory region, we looked for a specific change, when that region hit a certain value. This might be really useful for determining when a lock is reset or when a counter reaches 0 and so on. So there are some interesting uses if we can look for particular values in the memory region as well. So this is one way to address the concern about managing cached data. But so far what we've assumed is that all compute nodes can access all data. So any compute node can read or write any part of the data set or the metadata that is used to get to the data set. But there's a whole spectrum of sharing options out there that maybe we should step back and consider other alternatives before we declare victory on this particular question. And so in particular, let's think about the other end of the spectrum, a partitioned approach, which is the way that things are commonly done in distributed systems. If we were going to apply partitioning in a disaggregated environment, the basic idea would be to take the data and create partitions of that data set in disaggregated memory, and then assign ownership of that partition, each partition, to a compute node. Now, because the compute node has exclusive ownership of the partition, it's the only one that's going to be updating it. So it can go ahead and cache that data as it sees fit without worrying about having to maintain its cached version as the most up-to-date version. It just will be because of the exclusivity. So that's great for common case performance. The potential downside, though, of this approach is that if in fact we need to reconfigure the system because maybe a compute node dies and we need to do a repartitioning, that's going to entail a lot of reorganization of the data in disaggregated memory, which may be costly. So again, if you think about it, this is an all or nothing approach. So we can either share nothing or share everything. There's middle ground here that we should also explore. And that's something that we've been doing in a system that we call disaggregated partitioning. And this is joint work with folks at UT Austin, as well as HPE and VMware. So the basic idea of disaggregated partitioning is that compute nodes partition the ownership of the data, even though the underlying disaggregated memory allows them to have visibility on the entire data set and all of the metadata that governs that data set. And so, again, like the partitioned case, we're able to have that exclusive ownership of a partition, which means that we can cache, however we see fit, and we can very aggressively cache, which will allow us to improve read performance in the common case. Reconfiguration in the disaggregated partitioning case, unlike the traditional partitioning, reconfiguration is actually really cheap. All you have to do is just reassign the ownership. And if the previous owner is still alive, that owner is going to have to flush any of its outstanding updates and drop its cache. But generally, there's not really any need for expensive data reorganization in the disaggregated memory. And so because this is a really lightweight reconfiguration operation, you can use it for a wide range of different reasons. So you can use it to handle the failure of a compute node. You can use it to handle when you need to add compute nodes or remove compute nodes. Similarly, even when you need to rebalance the load because of a really skewed workload. So it's a really, really interesting mechanism that we can then use to solve a number of different questions. We've prototyped a disaggregated partitioning system that's a key value store. We call it DP store. And so the basic idea is that we use consistent hashing for assigning the ownership. And because of that exclusive ownership, we're able to cache both pointers to data in the disaggregated memory, if we want to be space efficient. We can also then cache the data itself because of the fact that the owner is the only one that's going to be updating that data. Now, our comparison is going to be against a system called Clover, which was published in Usenix ATC in 2020. Clover is a shared everything system where all the compute nodes can access all of the data, both read and write. And because of that concurrent sharing, they employ a multi-versioned data solution that's used in the disaggregated memory. Compute nodes, because there can be multiple updaters, compute nodes are only going to be caching the pointers to the key value pairs, not the data itself. And in the event of a cache miss, the compute nodes will contact a metadata server for help locating the data that they care about. So let's compare the performance in the common case between DP Store and Clover. And so what we see here is, for the YCSB workloads, we are looking at the relative throughput of DP Store relative to Clover. And so what we see is that that DP Store really outperforms Clover in all of these different workloads, regardless of how much, what's the read-write percentage that we're seeing. And that's primarily because of the fact that disaggregated partitioning allows that exclusive ownership so that we can cache the values of the data, not just pointers to the data. So there are hits in the cache that don't incur any far memory accesses in DP Store, which allows it to get very high performance. In contrast, Clover requires at least one traversal over the network to far memory in order to retrieve data, potentially more because of the multi-versioned data approach that it uses. So they might have to, compute nodes might actually have to walk the chain to find the most recent version of the data. So disaggregated partitioning allows DP Store to get very good performance in the common case. It also allows the lightweight reconfiguration that I mentioned earlier. And so here's an experiment where we're running YCSB-B, and every 5 minutes, we're either adding or subtracting a compute node, starting with one compute node, going up to 4, and then going back down to 1 again. And so what we see is that DP Store is very quick at accommodating the changing number of compute nodes in the system. There's only a minor hiccup when performance drops slightly to allow the owners of the data to actually flush out their outstanding rights. But generally speaking, it's a very smooth transition, very lightweight reconfiguration. So this is just one way that we can potentially rethink how we organize systems in order to to overcome the challenges of sharing data that is being cached on the compute nodes. So our third challenge is about data movement. And as we know, data movement is costly. It's costly both in performance, the time to transfer the data, the cache pollution that might result from having a lot of data. It's also expensive in terms of the energy that's consumed. So this is a figure from an exascale computing report that was published almost a decade ago. And it shows that off-chip data accesses and data movement are orders of magnitude. They require orders of magnitude more energy than on-chip accesses. And although this data is somewhat old, similar trends hold today. And in fact, a more recent study actually explored the energy that was consumed in Google mobile applications. And they found that over 60% of the overall energy was devoted to data movement, often for pretty simple functions. So things like data packing and unpacking or quantization. So this is just further evidence that something that we already know. Data movement can be very costly. The other unfortunate truth is that data movement might not actually be necessary in some cases. So, we talked a little before about inlining data structures that pack a bunch of values together. And so in the end, you end up having to transfer the entire set of values, even though all you really care about is one of them. So there's this amplification problem that can happen depending on the choices that we make in designing our data structures. Another issue is, some applications like databases, they perform filtering at the application level. They'll read a bunch of data, apply filters on that data, and then discard some fraction of the data that's not responsive to the query at hand. So data movement's expensive, and we might not actually need to do it. So wouldn't it be great if our disaggregated memory were smart enough to help us manage that data movement and to limit the data movement? So when I say smart disaggregated memory, what I mean is smart both in terms of the level of semantic abstraction that the memory presents, as well as the computing capabilities that are required to get the desired semantics. So let's dive into that a little bit more. So this is work that I've been doing with Dejan, as well as our colleagues at ETH Zurich. And so what we are proposing is to raise the level of abstraction of smart memory from a memory interface to a declarative data interface. And so the idea would be that applications would access data collections as a unit. So this is a really good match for the way that data science applications currently manipulate data with data frames and whatnot. So data collections are now the unit that we care about. And the idea is we're going to borrow a concept from the database community, that of views. And so the application is going to see a logical representation of this data that may or may not be the same as the underlying physical representation. And the way that we're going to achieve this view concept is through a set of operators that can be applied inline on data path operations by this smart disaggregated memory. So in order to allow us to do this inline without incurring too much overhead, the kinds of functions that we're thinking about are either stateless functions or things that are minimally stateful, things that don't really require a lot of intermediate results to be stored. And in particular, we're thinking about fixed functions rather than user-defined functions, for similar reasons. We don't want to have to worry about large computational requirements or memory requirements, for these functions. We also don't want to have to worry about buggy or malicious user code that we need to manage in the system. So stateless or minimally stateful fixed functions are what we are most interested in this context. And so if you look across a range of different applications, there are some general purpose data-centric functions that are pretty common across all of those different application areas. And those are the things that we want to target with this work. And so in particular, there are three categories that we've been looking at. One is filtering operations, so things like predicate selection, regular expression matching, numeric precision reduction, and so on. Those are great at potentially reducing the amount of data that's actually sent over the network. We also have transformations that might reduce the amount of data that's being sent. So compression is one example of that, as well as aggregation operations. So things like mins or maxes or averages, that sort of thing. Transformations also may be very useful for doing things like encryption inline that will help with the security of the system. And then finally, a category that kind of harkens back to an earlier part of the talk is the notion of smart addressing, the ability to do strided memory accesses or maybe even matrix transposition. And all of these things are things that are common across these different application areas. Now, in order to raise the level of semantic abstraction to this notion of a data interface, we're going to need some processing capabilities in the memory. And so the way that we've been approaching the problem is to use a smart NIC that's actually implemented in an FPGA in order to do this processing. And so the idea is that we implement the operators in the FPGA and allow them to operate directly on data that's being read from the memory as well as written to the memory. And they're exposed through RDMA verbs that are extended to actually implement the operator logic. We've prototyped this idea in a system that we call Farview. And so the basic idea is that the FPGA is divided into regions where each region will implement the operator or operators that are necessary to satisfy a client request. Now, these regions are actually dynamically reconfigurable, so we can change which operators are currently being used depending on what the workload looks like. The FPGA also includes modules for the memory stack, being able to access the FPGA local memory, which is playing the role of disaggregated memory in our prototype, as well as a network stack that's being used to implement the RDMA operations and RDMA verb extensions. So we've implemented this on a Xilinx board and using an open source FPGA shell that was published at OSDI last year. Our comparison point is a compute node that is just kind of a traditional general purpose CPU that's equipped with a commercial NIC, in particular a Mellanox Connect X5. So I want to focus the discussion of the evaluation results specifically on filtering. And in particular, we'll look at two different experiments here. So the first is one that looks at reduced precision operations. So the idea is that we're going to read 8-byte data and then quantize it down to as little as 1 byte worth of data. And in the Farview case, we're going to apply that precision reduction at the memory in the smart NIC. And then for the baseline, we'll actually read the data in its entirety and then apply the precision reduction at the compute node. So what you can see is that Farview definitely improves on the full precision reads as it actually is able to reduce the precision closer to the memory. So we're actually able to really benefit from that in terms of the time that it takes to transfer to read 1,000 of these data elements. In contrast, the traditional approach of using the commercial NIC and the compute node, there really isn't any benefit for being able to read the data at more reduced precision. So what we see is that by pushing this filtering logic closer to the data, we're able to achieve performance benefits. Similarly, we can look at predicate selection, which is a common operation in databases. And so here the idea is that we've got a set of data that we're then trying to return only a fraction or select only a fraction of that data, ranging from selecting all of the data, 100%, all the way down to selecting only a quarter of the data, 25%. And again, the comparison point is a CPU where we're transferring all of the data and then applying the selection at the compute node. And so what you can see is that pushing the filtering then closer to the data really improves the performance, especially as our operations get more selective, as we throw away more of the data. So these are just a handful of examples of how increasing the smartness of the disaggregated memory allows us to reduce data movement. It also has many, many other applications, and we'll talk about those in some of the forward-looking work as well. So great opportunities, I think, for exploiting the intelligence of the disaggregated memory. So switching gears, let's stop talking about challenges and then let's talk about an opportunity that disaggregated memory provides for us. Now, in particular, one of the things that I mentioned earlier was that disaggregated architectures really provide separate fault domains. So just because a computation or the node that it's running on dies, disaggregated memory is still going to be alive and available to the other compute nodes in the system. So if a computation that's running on that failed compute node was able to actually push its state out to the disaggregated memory, then some other node could actually take over for the failed computation. And this is a partial failure model that really allows us to avoid an overall shutdown of the entire system. So that is an improvement over a traditional scale-up system where a compute failure would probably take the whole machine down. And it's also an improvement over a scale-out kind of an environment where if you don't make your data redundant, the failure of a compute node might actually take out part of your data set. So with that backdrop in mind, let's think about how we would actually provide resilience for applications that are running in disaggregated memory. The kinds of applications that really thrive in disaggregated memory are ones where the data sets are really large and they're long-lived. And so as a result, they're not really very amenable to traditional resilience techniques like checkpointing. So the nice thing is that I think there's some tools in our toolbox of disaggregated memory that we might be able to use to address this challenge. And in particular, when I was at HPE, we worked on a system called Memory-Oriented Distributed Computing, or MODC. And so MODC is a framework for writing resilient applications for disaggregated memory architectures. And it borrows ideas from things like task-based programming to allow us to achieve very fine-grained recoverability without requiring us to do explicit checkpoints. It also relies on an underlying runtime system that will schedule the tasks to satisfy any dependencies and also restart the tasks that fail along the way. And we'll talk more about how that happens on the next slide. So now I just have to say one caveat here, so as to avoid confusion. In contrast to the Farview system that I talked about in the last section, where this memory was smart, here we're assuming a system model where the disaggregated memory doesn't have any computational capabilities. So it's not possible to offload some of the logic that we need into the disaggregated memory system. Instead, we're going to use the disaggregated memory to store data structures that are shared amongst all the different participants. And we're going to use those data structures to encapsulate the global state of the runtime system. And the way that we'll access those data structures is using the one-sided operations of the interconnect, as well as lock-free programming techniques in order to allow us to have concurrent access to those data structures. Okay, so a task-based programming model, what does that mean? Well, the basic abstraction is one of resilient parallel jobs and tasks. So an application is designed as a set of execution units or tasks, where those tasks need to be idempotent. So given the same input, they have to produce the same output, regardless of where they're running, which node they're running on in the system. And each task is going to read its inputs from the disaggregated memory and write its outputs to the disaggregated memory. There may be dependencies between tasks, so data dependencies in the sense that the output of one task might be the input of another task. There may also be control dependencies because a collection of tasks might need to finish execution before another set of tasks can begin execution. So we introduce the notion of a job to handle those control dependencies. The task graph doesn't actually have to be determined a priori. It's possible for that task graph to be constructed as part of the execution in a dynamic parallelism kind of model. So tasks can create other tasks, and this is really useful for being able to do recursive decomposition and other kinds of popular parallel programming models. The application programmer is responsible for specifying the size of the tasks as well as the dependencies between the tasks. So that allows them to have control over how fine of granularity of recoverability that the application will have. So all of this is supported by the underlying runtime system. And so, of course, there's not enough time for me to go into a lot of detail about how the runtime system works, but I just want to give you a flavor of how we're using these data structures under the covers. So in particular, let's think about the resilient task scheduler. So the idea here is that we're using shared data structures in disaggregated memory to manage the dependencies between the tasks, as well as manage the overall scheduling of those tasks. So whenever the dependencies of the task are deemed to be met based on the analysis of these data structures, a task is ready to be executed, and it'll be put into a work queue for a worker to execute. And the way that these work queues are implemented are, it's actually a double-ended queue data structure that's stored in the FAR memory. And so the idea is that the owner of this queue is going to consume tasks to be executed from its end of the queue. In addition, because of that dynamic parallelism model, it may actually be spawning tasks into that end of the queue as well. Now, in addition to the owner being able to access this queue, it's also possible to do work stealing. So idle workers can look around and steal work from the other end of the queue. And so this might happen because an idle worker detects that a worker has failed, or because a worker is just overburdened with too much work to do. And so I can't really go into the details of this, but suffice it to say that the log-free programming techniques and the data structures really allow us to ensure that each task is executed only one time, based on careful, sort of tracking of state. In general, this is one example of data structures that allow computations on different compute nodes to actually coordinate with one another. We've implemented a prototype of MODC that implements this dynamic parallelism model and the runtime that manages all the task dependencies and the task execution and the worker coordination. It detects failures and so on. And so that's going to be our comparison point. And then our baseline is going to be a more traditional approach to writing a resilient application, in particular using both MPI and checkpointing. So the MPI application will use more of a static form of parallelism where the task graph is known ahead of time. And it's going to express its control dependencies as MPI barriers, and it'll use checkpoints to get its resilience. And then to make this as much of an apples to apples comparison as we possibly can, both of these implementations are going to use the same data access methods. And the way that we're going to emulate this is on one of the big scale-up multiprocessors, the Superdome X. And so the idea is that one of the 16 NUMA sockets is going to play the role of the disaggregated memory, and then the other sockets will play the role of the compute nodes. So our case study is going to be Pagerank, which is an iterative graph analysis algorithm. And so Pagerank basically at its core is, if you represent the graph as a matrix, at its core, it's really just a lot of sparse matrix vector multiplication operations. So what we're going to do is we're going to structure this application with two stages. Each job is going to represent an iteration of the Pagerank algorithm, and then each task is going to represent a smaller portion of the sparse matrix vector multiplication operations on a subset of the graph, subset of the matrix. And so we'll have a set of tasks that correspond to job one, which correspond to the first iteration, another set of tasks that correspond to the next job, which corresponds to the next iteration, and so on and so forth. So to compare the different fault tolerance alternatives, we're going to run Pagerank for 10 iterations, and we're going to inject failures in certain iterations. And our assumption here is that we're doing non-shrinking recovery. So there's a standby, a hot standby worker that's ready to take the place of the failed worker, so that we always have a constant number of workers operating on the algorithm. So what you see in the graph here is on the x-axis is the iteration where we injected the fault, and then the y-axis is the overall execution time, including the time to handle failures and any recomputation that's necessary to complete the 10 iterations of Pagerank. So what we see is that for failure-free execution, both MODC and MPI without any checkpoints perform comparably to one another. When we add in the checkpoints for the MPI application, there's about a 10% performance hit that is due to the need to checkpoint the dense vector that is used in the sparse matrix vector multiplication operation. When we start injecting failures into the system, what we see is that the MPI application, the execution time really depends on when we inject the fault relative to when the last checkpoint was. So our assumption here is that checkpoints are happening every 4 iterations. So you can see this sawtooth pattern in the execution time for the MPI application, depending on when the last checkpoint took place. In contrast, the Mozzie recovery time under failures is really only 1% longer than the failure-free execution, so much so that you can't even really see it on the graph because it's pretty much right on top of the failure-free execution curve. So overall, checkpoint-based recovery is significantly slower than the fine-grained recoverability that we see with this Mozzie approach. So this is just one example of some of the opportunities that the disaggregated architectures will provide to us in the way that we structure our systems. There's been a lot of really great work across the community, in dealing with remote memory and dealing with disaggregated memory. But I feel like we've really just scratched the surface in all of this. And I think that there are a number of interesting areas that we could potentially address in the future by exploring things more. And really opportunities up and down the stack. So if we start at the top and work our way down to the bottom, on the algorithm perspective, disaggregated memory architectures present a really, really large pool of shared memory. The memory is, in fact, shared between the compute nodes, and potentially it's also persistent, depending on how you choose to construct the system. So, with those 3 interesting new opportunities in mind, what can we do in our applications in order to exploit those characteristics? So, we saw an example earlier where you can pre-calculate results in really large data structures in the disaggregated memory. You might also be able to use really large, in-memory indexes to answer interesting questions, or use the disaggregated memory to do workflow communication between stages that are running on different nodes. You could even maybe ignore the coherence problem by taking advantage of recent work in machine learning algorithms that are tolerant of stale data. And so I think there are all sorts of interesting possibilities here to really think about, be creative about how we organize our applications to take advantage of these architectures. In the data structure space, I talked about some specific data structures. What are other specific data structures that make sense in a farm memory environment? And maybe we can even step back a little bit and figure out what are general principles for designing data structures that are going to make sense in this environment. From a programming model perspective, in the Mozzie work, we looked at task-based programming models. Well, application writers might actually welcome the opportunity to have some help in figuring out what the right task size is. So, for example, could program analysis techniques or compiler techniques actually help us to figure out, when is a logical point when computation has reached an interesting point in terms of its data dependencies, and maybe help us to right size the tasks for this resilient task-based model. And other synergies, I think, also exist between disaggregated memory architectures and work that's happening in the cloud with serverless or functions as a service kind of computational models. And so those models will publish all of their state to a shared data store. Right now, that's a fairly slow data store, but if we can make the data store a memory data store, I think there's an opportunity there to really improve the performance of the function as a service kind of workloads. From a system software perspective, it seems like there are probably a lot of interesting techniques from the concurrent programming community that we might be able to apply to this particular context for coordinating activity between different nodes. So for example, think of an MCS lock where you try and make much more efficient and localize the accesses for a lock rather than having to invalidate caches and whatnot. So that's how an MCS lock works. What's the moral equivalent in a disaggregated memory space? It seems like there are some parallels there that we should explore. Both lock-based data structures and lock-free data structures, can have issues when they're under high contention. And so there is a class of coordination-free approaches that actually might be an interesting thing to explore in the context of, looking for scalable ways to maintain concurrently updated data. And then finally, far memory is really a new point in the spectrum, the hierarchy of memory and storage. And so, how do we manage that hierarchy and make sure that the data that we care about is in the appropriate tier when we need it? When it comes to smart memory, smart memory, I think, is this opportunity for us to explore a wide range of different functions. And in one particular area that I think is especially potentially fruitful is that of ensuring that the disaggregated memory itself is fault tolerant. And so in particular, I think that memory intelligence could actually be used to potentially handle replication or erasure code calculations, potentially create snapshots, or even maybe do background data scrubbing operations in order to improve the health of the overall disaggregated memory system. There may be other guarantees that smart memory should provide, so things like transactions or logging or versioning. And so it'd be interesting to explore that as well. And then, finally, questions around what the API should look like to smart memory. I proposed data collections as an API. What are the additional operators that we should be looking at there? Maybe there are other APIs that would make sense as well in the context of smart disaggregated memory. And then finally, I think there are some really interesting opportunities for hardware-software co-design. In particular, we've described a bunch of different functionality that we want the smart NIC to be able to to provide for us. What are the computational requirements of a smart NIC, and are there additional capabilities that might allow us to do even more? And then also there's work in the architecture community that's starting to explore, delegating operations. Actually, this is an idea that's been around and come around again, for doing processing in memory. And so particular people have recently been looking at, copying data in memory as well as doing bitwise operations. And so I think there's some interesting, opportunities to figure out what additional functionality might be able to be delegated to those devices. Okay, so wrapping up, data growth and the urgency of needing to have answers now really is meaning that the memory is the bottleneck of current systems. And fortunately for us, there are fast network technologies that allow us to consider the possibility of applying resource disaggregation to memory. There are a number of benefits to this. It increases our effective memory. It allows us to independently scale things. And it allows us to have separate fault domains that we can exploit for providing application resilience. There are definitely some challenges, and I think we've got some initial ideas for how we might be able to address them, but there's certainly more work to be done, and also a lot of really interesting open questions to still be answered. And so with that, I'll conclude and encourage us all to think outside the box.
Thank you very much, Kim. Great talk. I always learn whenever you present. We have a ton of questions, so let me start. I'm not sure if you had a chance to look at it, but let me start with the first one. Was the machine a success or a failure? What were the learnings? Why did the research project not result in broader adoption? Does the emergence of CXL change the viability of memory disaggregation?
Whoa, okay, one at a time. So so taking the first one, I do believe that the machine project was a success. We demonstrated that it's possible to build a very, very large scale disaggregated memory architecture. Both from a hardware perspective, we demonstrated the potential of applications to exploit the characteristics of that architecture. And I think, if you look at some of the commercial products that HPE and other companies have today, you'll see versions of, something that looks like a machine, basically a modular architecture that allows you to access memory from across an interconnect. And so in that sense, I think that it was a success. And so I think, let's see, that was the first question. What was the next question?
You answered second, third, and fourth. Fifth is, does the emergence of CXL change the viability of memory disaggregation?
Change the viability. So I think, there are multiple interconnects that I think make disaggregated memory more viable. And so, the standards are evolving over time. Initial versions of CXL are primarily, concerned with point-to-point kind of coherence between processors and accelerators and whatnot, and storage devices. And I think future versions are then reaching outside of the box. And so I think that that will increasingly become interesting from the perspective of looking at rack scale kind of architectures. Gen Z is already in that space, and already looking at things at the rack scale and potentially even larger. So I think that both of those interconnects represent interesting options, as does RDMA. And that's, RDMA is something that, has been around, and, we are already learning how to use it and to, take advantage of the operations that it provides.
Okay, next question. Distributed shared memory models such as Ivy and Munin have been very useful. I wonder if only a few of us remember those. Okay, there are more questions. However, putting together the data is based on the needs of the computer node. Are there multiple data sets that are equally likely at a processing step prefetched in this model?
I'm not sure I understood the last part of the question. So certainly there, people are rediscovering the notion of distributed shared memory. And so we've seen a number of systems that are re-exploring this idea, I would say even in the last 5 years, based on these fast networks. And so, so there are things that are looking at persistent distributed shared memory, as well as, sort of looking at, at a wide range of different alternatives, and providing different kinds of interfaces to it. And so I think that, that is one way to organize data across outside of the box, use another box's memory and borrow another box's memory. That has some challenges associated with it because, there may be an application computation running on that other node. So, that node might be busy doing other things. And so as a result, that's why most of the work that I've been working on, has really focused more on the disaggregated space where the memory pool is distinct from the compute nodes. The last part of the question, I wasn't sure I fully understood that. Can you repeat that?
Yes. Are there multiple data sets that are equally likely at a processing step prefetched in this model?
Multiple data sets. I think I'm not sure I fully understand the question. And so I think, they're certainly possible to have different data sets that, if one knows enough about the application to be able to prefetch the data into local memory, then, that can be a very effective way of organizing the computation. I think many of the applications that people care about that have really large data sets, we don't always know what data we're going to be accessing. Maybe it's a graph traversal, that is going to be randomly sort of looking throughout a cluster kind of an environment. And so it might not be possible to always be able to prefetch the data that we care about into our local memories.
Okay, then there's a comment about tidal scale. I'll leave you guys opportunity to read about it and move to the next question from Tom Coughlin. Can you make some comments regarding working with various types of memory, e.g. DRAM and Optane?
Sure. So I think, persistent memory is a really interesting technology. Originally, I think we were all so excited about the prospect of having, persistence at memory speeds. And I think that that's still a very interesting thing. But another interesting aspect of the persistent memory technologies that we see today are that they're denser actually than DRAM technologies. And so as a result, we're seeing almost as many people interested in using the memory as a denser form of memory, even if it's for ephemeral data, as for persistent data. And so that's been an interesting observation that I think I hadn't really thought about when we were going into the question of how do we use persistent memory. And I think there are also questions about what kind of memory does it make sense to use in a disaggregated memory environment. I think that there's value in using persistent memory because it's an opportunity for you to actually store your data persistently across the fabric to survive the failure of your compute node and then be able to come back to it later on. I think that there is also a role though for having DRAM that's across the interconnect, especially if you can apply some of these filtering or transformation operations to reduce the overall cost of accessing the memory.
Okay, we have 4 more questions and 1 more minute, so I'll be very quick. Thank you for your lecture, slide 53. What if we have a philosophical device at the bottom of the stack that is the farm memory model that makes the necessary reconfiguration happen? What can this reconfiguration be based on?
And so by necessary reconfiguration, I'm not sure I understand what
Okay, so
that
perhaps we
means.
can move on the next question, which is defined as dumb question.
No dumb questions.
Does CXL need to move beyond cache coherence everywhere to be useful for large-scale FAM?
I think if people can figure out how to do cache coherence at large scale, bring it. I love that idea. I think that that's a very, very challenging problem, though, and so I don't think that that's practical at really, really large scales. And so, in that sense, if we really are talking about a very, very large fabric-attached memory environment, we're probably going to have to cope with the fact that there isn't going to be that cache coherence.
Okay. Next question. With memory fault rates increasing, there is a risk that disaggregated memory could become a single point of failure. Is stronger memory RAS the answer? Reliability, availability, serviceability.
Mm-hmm.
Are there viable software resilience approaches to tackle this problem?
So I think, if we want persistent disaggregated memory to be the new storage, it needs to behave like storage. It needs to be able to store things and remember them. And, even if it fails, still remember them, right? So there's a role, I think, for applying many storage-like ideas and RAS ideas to the disaggregated memory environment. Whether we can do those in software remains to be seen to me, because memory operates at much faster speeds than than storage does. And so as a result, I think if we can have a hardware-based solution to that, then that's going to allow us to use the memory as the memory that we want to use it as, if that makes sense. And so I think that there's a role for hardware software co-design there, and potentially for smart memory as well.
Okay, and the last written question: wouldn't disaggregated memory require to break current operating systems concepts like page cache? Are we not going to need new OSs that use disaggregated memory cleverly?
Well, I think that's a real interesting question. If you look in was it SOSP or OSDI? I think OSDI in 2018, there was a paper called Lego OS, which is an entire operating system built for a disaggregated memory environment. So yes, I think that there are interesting operating system innovations that we're going to want to take a look at as we start to explore this idea further. In terms of, can we just, there are also studies that have looked at using the disaggregated memory merely as a swapping device, so, as a paging device. So I think it is possible to, to make more incremental steps and use the disaggregated memory even with an existing operating system, though.
Okay, is there anybody else who would like to ask a question in person? Maybe one or two more questions. Okay, having heard none, Kim, thank you very much. Extremely interesting talk, and we'll make both slides available and the video recording.
Great. Thank you so much. I really enjoyed the conversation.
Bye.
Great.